So when we met last time, we didn't do a lot of talking about various kinds of components. And we haven't really talked that much about our various kinds of components yet. We're going to start with that kind of concept today. And the way we sort of by default describe the various components that we have in electrical engineering, kind of the default way to do that is with a voltage-current relationship. Okay, and various different kinds of elements might have different relationships like this, and so that's kind of what we're going to focus on today is voltage-current relationships for elements. We'll start with kind of what might seem relatively obvious, but we'll go ahead and go through it anyway. We've already talked about how voltage is electrical pressure, right? It's what is trying to drive current through a material. And the current is essentially the response to that. The current will begin to flow through the material if there's a certain amount of voltage. So it would probably stand to reason, at least in most of our minds, it would probably stand to reason that if we apply more voltage, in other words, more pressure, we would expect that that would increase the rate of flow of charge through the material, right? That's kind of, that would make sense to me even if I didn't know anything about how it really worked. And it turns out, for most materials, that is how it works, okay? I figured I would start with this kind of, we don't do a lot with this kind of an analysis in here, but we really do actually have some ways for many kinds of materials to describe, relative to the size and shape of the material, how much it will sort of resist the flow of current through it given a particular voltage. And the way that typically works, it's going to be related to three parameters, okay? One is how long is the piece of material? If you have to push current through a longer distance, that typically increases how much voltage it takes to push that current, a given amount of current, let's say. So length is one aspect. Another aspect is called resistivity. That is a material property that is essentially, it varies between different kinds of materials. We're very used to copper wire. Copper is used because it has very, very low resistivity to it. It's a material property, so copper is really good at that. As a matter of fact, there's really only one element that's better, and it's silver. Okay? Copper is the second best of the various kinds of elements at conducting electricity. And then the third aspect that's important with respect to a material's ability to conduct electricity is the cross-sectional area of the conductor that's carrying that current, okay? And that kind of stands to reason too. If you give it, you know, a nice big hallway to march down, you would expect that that probably would lead to fewer destructive interactions between your electrons and whatever's in that sea of electrons as it goes through the conductor, okay? So all these things I think are relatively intuitive, and even the equation that I'm about to write up here is relatively intuitive. This ratio of voltage to current, V over I, is related to these physical parameters for a conductor according to the resistivity, rho, that's a letter we give to that, multiplied by the length divided by the cross-sectional area. So this makes sense because more resistivity means you're probably going to need more voltage to push a particular amount of current. More length means you're going to need more voltage to push a particular amount of current. But more cross-sectional area probably means you won't need as much voltage to push a particular amount of current, okay? And it turns out that if you look at all of these different values, for most materials, they aren't variable, right? So resistivity remains relatively constant. If the size and shape of the piece doesn't change, then things like cross-sectional area and length won't change. So this thing ends up being relatively constant, and because it's relatively constant, what shape are we going to have on a plot of V versus I? What would you say? It's probably going to be a straight line, right, for most materials. And so this is the way a lot of things behave, and so it stands to reason that we should probably sort of focus on this type of material or this elements that behave this way at least for a few minutes, and that's what we're going to do today. Okay, turns out that this is such a common way for elements to behave that we are going to actually give the slope of that V over I line, right? The V versus I line that I just drew on that plot right there. We're going to give the slope of that line a name. All right, that's going to be called resistance. Okay, so up here where I had V over I equals rho L over A, I could also say that this is going to be equal to R, where I define the letter R as being resistance. Okay, and it is that ratio of voltage over current. That is actually what most people call Ohm's law. So it's really not complicated. Ohm basically kind of identified that, hey, you got more voltage, it's going to push more current, right? And if you have a material where that's a linear relationship, then something as simple as Ohm's law holds with no problems. Okay, so V is equal to IR is Ohm's law, and I don't have a ton more to say about it, honestly, because that is, you know, it's a starting point for a lot of things we do in electricity, but we'll get into some examples here after a little while. Let's look at the units, though, of resistance, because that's also going to hopefully be interesting. Since it's defined as voltage over current, one of the ways that we can deal with the units is, okay, we can actually think of typical units for each one of those parameters, right? So voltage, how do we measure voltage? Volts, okay? Again, that's one of the only ones where the name of the unit is essentially the same thing as the name of the type of quantity. So that gets confusing sometimes, but we'll mention it a couple times so that we don't get too confused with it. So think about a volt, and then how do you measure current? Amps or amperes, right? So volts over amps is the type of units that we would have with V over I, and that is going to be the unit that we have here, and that unit that we're going to define is called ohms, and we give it the letter uppercase Greek omega. Okay, and I'll write over to the side over here that this is ohms. Okay, again, that may not be a surprise to many of you, but you know, we'll cover all the bases here. Now, there's another thing that may not be as familiar to you just yet, and that is it was kind of arbitrary that we defined the ratio as being volts over amps or voltage over current, right? We could just as easily have said for a particular amount of voltage, make that the horizontal axis, and you will have a particular amount of current and make that the vertical axis, right? And we could have had a different slope there, and we would have measured it as current versus voltage, right? Well, it turns out both of them basically get at the same thing. It's just they are reciprocals of one another. And so we give that a name also, that parameter of essentially the ratio of current to voltage. We give that a name, and that is called conductance. Okay? And so the units of conductance, that would be amps per volt, right? And this actually has also been named. It is called a Siemens. Capital S, okay? That's Siemens or Siemens. That is how we measure conductance. There are actually in some older textbooks, there's another way to name this. What they did is they took the letters of ohm and they reversed them, and they called it a mho, okay? So I very seldom see that anymore, but there are some books I have seen where they actually mention that this is a way that you can describe conductance. So anyway, this is kind of the background. Let's look at components that actually behave according to this linear relationship between voltage and current. Okay? We call those types of elements resistors. Okay? A resistor, like I said a second ago, it is an element where the ratio between voltage and current is expected to be relatively constant. Okay? I have a whole you know, sort of array of pictures over here to the side to kind of show you here is what resistors often look like. I don't have an exhaustive picture list over here or anything, but you can kind of get the idea that this is what resistors might look like. One of the things that controls what a resistor looks like is how much power it is expected to have to dissipate and how it is going to get that energy out of itself once it begins to dissipate that power, right? Energy is this complicated thing where you can't just sort of wave it goodbye, right? It gets out in some actual tangible way. And so with resistors, what they do is they take electrical energy and power and they convert that electrical energy and power to what? Heat. And if it's kind of continuously producing heat, which is essentially thermal energy, what happens to temperature if you don't get that heat out of there somehow? That temperature will keep rising and rising, and eventually some of how you thought those materials might behave at one temperature, they might not behave that way anymore at a much higher temperature, right? So a lot of the look and feel of what these resistors look like has more to do with how much energy they are expected, or the rate of flow of energy, I really should say, that they are expected to dissipate. That kind of controls what they look like physically, right? It doesn't necessarily have as much to do with the actual resistance value, which is sort of the slope of that V over I curve, okay? One place where many of you have probably seen resistors is on your stove, right? Some of you have electric stoves in your house, and you see this little coiled up thing on top of your stove. That is essentially just a resistor, and it is designed to plug into electrical power from your house, and it's designed to produce heat based on pulling that electrical power from your house. I could have also pulled the element out of a dishwasher or in your oven. There's a lot of different places where we see this, but those are essentially just resistors. All right? So does that mean that every element out there has to be a resistor? Okay? And if some of you are saying no, I agree with you. We don't want to go too far and assume that every single element that we see out there is going to have this linear relationship that crosses at zero for V over I. That's kind of what a resistor does, but not every element necessarily behaves that way, okay? And so there's a couple of examples I put on here, and a couple of those actually were on this little list of things up here. You'll notice over to the right, it calls these nonlinear resistors over on the right side, and a few of those look like they are essentially resistors designed to sense things, right? A thermistor. This is a light detecting resistor, right? A varistor resistor or a flexible resistor. Those kind of look like they have the goal of being some kind of a sensor of some kind. So that is definitely a category of resistor that we need to be aware of, that sometimes you can influence what the resistance value is of the element based on some external stimulus of some kind, right? Like temperature, light, a lot of different things. But there's also another kind too, where there is a nonlinear relationship between voltage and current, and a big prominent example that's like that would be a light bulb. When I was young, so my father was an electrical engineer, and so partly because of that, he gave me a multimeter when I was probably 7 or 8 years old, and kind of showed me a little bit of how it worked and stuff. So that was very fun for me when I was very young, trying different things. And he even taught me a little bit about Ohm's law, right? Showed me kind of the basics about Ohm's law and that kind of thing when I was real young. So I had my multimeter, and I also had this little box full of little stuff that I could use my multimeter on, okay? One of the things I had was a light bulb. So what do you think I did? I'd learned Ohm's law, so this should be kind of like a resistor, right? Okay, so I took my multimeter and I measured resistance across the two terminals of a light bulb. What do you think I found? Okay, my multimeter said that my light bulb had almost zero resistance. Okay, but my dad had also told me that you don't want to plug things with zero resistance into some kind of a voltage. And this caused me some distress, right? Because I wanted to plug in my light bulb into my battery that I had there, and I knew it was not non-zero voltage, right? So I wanted to plug it in. And, so I actually had to go to him and ask what was going on. I actually wasn't very satisfied with his answer. I'm not sure he even knew what was going on. It took me later in life to realize what was going on with the light bulb, okay? How does a light bulb produce light? Okay. It makes something really hot in there, right? There's a little piece of wire in there, and its job is to actually get to really, really high temperatures so that it glows, right? And then in doing that, it will start to emit these photons, and we get to see that as light, right? Well, it turns out that there was this temperature-dependent relationship that was going on with the material of the light bulb that I was not familiar with, okay? And so if you think about what the VI relationship would look like for a light bulb, what do you think it might look like? Okay, at very low amounts of current, you are probably not producing enough power. You're not introducing enough power into the filament of the light bulb to make it get very hot. Okay, so at first, it starts being a very low slope, something like this. But as you begin to increase the amount of current, so you start ramping up the voltage a little bit, start increasing the amount of current, instead of it being a straight line, the curve will actually look something more like this. Okay? And that is because as that filament begins to heat up, that changes the resistivity of that material and starts making it more resistive. Okay? What does your multimeter do to measure resistance? Do you know? Okay? What your multimeter actually has to do is it has to introduce a little bit of voltage across the element that it is testing, and then measure what? How much current flows, right? Now, it doesn't want to waste a bunch of energy on that, so it's not going to introduce a really high value of voltage. It's going to introduce a very, very low value of voltage, and then measure a very, very tiny amount of current, take that ratio, and tell you what the resistance is. So when I was measuring the light bulb when I was a kid, what was it? Where on this curve was I measuring that light bulb? I was way over here, right? I was kind of, maybe way over here, and I was saying, man, that is, almost like it's just a wire. And truth is, it really pretty much was way over there, pretty much just like a wire. Okay? But then you start introducing more voltage. Now, when you measure that slope, you're up here, right? And each additional amount more that you add on there in terms of voltage, it's not going to push as much current per unit of voltage, right? And so that's why the light bulb behaves like it does. Okay? All right, so that is an example of something that's nonlinear. There's a bunch of other examples out there too, but I just wanted to sort of complete our discussion of voltage versus current relationships in this way so that we don't get the idea that everything is a resistor. Okay? All right. Now let's move on, and there's another thing that these elements can depend on. Okay? Time. Time is another factor that can control how elements behave sometimes. Two big examples of this that we are going to see in this course are inductors and capacitors. And I've put a little textual description up here of how each of those elements behaves with respect to its voltage-current relationship. And all I'm really going to do is just say this for right now. We're going to get much deeper into that once we get into inductors and capacitors later in the course. But here it says, applying a steady voltage causes a constant rate of change in the current flowing through an inductor. Okay, if I was going to write that in math, what that would look like is that the voltage across the inductor is going to be equal to the inductance, which we're going to denote that with L. We'll get to more of that again later in the course. But then we would do di dt, right? So how much voltage we put across it doesn't control how much current, it controls the rate of change of current. Does that make sense? For capacitors, it's kind of similar, but works just a little bit differently. It says applying a steady current causes a constant rate of change in the voltage across the terminals. If I was going to write that with math, it would basically say that the current flowing in a capacitor is going to be equal to the capacitance value C multiplied by dV dt. Okay? So I'm not going to, again, go super deep into this right now, but I want you to kind of have this idea that there are other kinds of elements that are out there where there is a voltage-current relationship, but it isn't just a straight line, right? It's something where it actually depends more on rates of change and such like that. So we're going to have to get into some calculus whenever we get there. All right? Cool. Here's another possibility here. Elements where voltage and current are actually independent of each other. Okay? I would say that is still a relationship. It's just one where it's maybe less interesting because one doesn't depend on the other. Have we already looked at elements in here that have an independent status between voltage and current? Okay. Like what? A voltage source, right? Let me draw that right here. Voltage source. Okay. A voltage source says I'm going to hold a particular voltage regardless of how much current flows. Right? So let's say, I'll just give it a value here. Let's say this is a 9-volt voltage source. What that's going to look like on a VI curve is basically no matter how much current, and I could show it as far as you want in either direction, you know, the value of 9 volts right there, no matter what happens, it's going to hold that 9 volts. Right? So it's just a horizontal line on there. Again, maybe less interesting, but we can think of it in terms of a voltage-current relationship. Okay? What else do we have? We have voltage sources. Current sources is another element that we've already identified, right? So we could draw one of those here, a current source. Okay? And for that current source, let's say I'll give it a value too. Let's say this is a 2-amp current source. Okay? What would that look like on this voltage current graph? Kind of the same thing except vertical, right? And it goes as far as you want, vertical, up and down as far as you want. And that value would be 2 amps regardless of what happens in terms of the voltage across that element. Okay? Now, a good question that might come up at this point is, what about dependent sources? Okay? So a dependent source looks like what? Something like that. That's how we draw it on a diagram. Dependent sources, it sounds like it's dependent on something, not independent, right? But what is it dependent on? Something else somewhere else in the circuit. Once that has been set, the dependent source is actually, at least by default, independent of the current. Like a dependent voltage source is by default independent of the current that flows through it, right? It might be dependent on a current somewhere else, right? That might happen. Or it might even be dependent on its own current if that's how it's set up. Like with a little, you know, you identify the current and then use the label on the side to make it dependent on its own current. You could do that, but it's not by default dependent on its own current, right? Does that make sense? Okay. What about a dependent current source? Is it dependent on its own voltage by default? No, again, it pushes the current that it will push based on the equation that you set up for that dependent current source, but it may, you know, it's not by default going to be dependent on the voltage that goes across that source. Okay? All right, questions yet? All right, let's move on to our next thing, and that is, now that we have identified this very broad category of elements out there that have this linear relationship between voltage and current, it may be handy for us to see if we can come up with cleaner, more easy to use statements of how much power those elements will absorb if we know just one of the key electrical parameters for that element. In other words, the key electrical parameters are typically voltage and current. And power we calculate with what? Voltage times current, right? So you need both of them by default, in general, you need both of them. But when you have a resistor, it sets a relationship between those two things, and so it allows us to eliminate one of the two electrical parameters, and we can figure out how much power just based on either voltage or current, as long as we know the resistance value for that element. Okay? So let's actually come up with what those might be. And I'm going to do it with these two sort of test cases right here. We have this current that we are pushing in this circuit on this left example over here. And I'm going to point out that this is a single loop circuit over here, right? There's only one loop there. So because I'm pushing a current of I in that loop in one place, it means that same current has to flow everywhere in that loop. There's no other place for it to go. Does that make sense? So I can take that current and say, not only is it the current that flows there, it's also the current that flows there. I can say that is I. Okay? If that's the current that flows there, is it possible for me to make an equation so that I can describe the voltage across that resistor, given that I know the current through the resistor? Okay? In other words, I can say, for that little element, I want to know what is the voltage across that element. Okay? Now, resistors, do they typically source energy or do they absorb energy? They absorb energy, and from what we looked at last time, things that absorb energy will generally have the current, well, not generally, always, things that absorb energy always have the current flowing into which polarity of terminal? The positive one, right? So because I see this current flowing down through here and that I have a good inkling that this thing is not supplying energy, it's absorbing energy, that means I can say that the voltage is definitely going to be that direction, assuming that I really does go the direction I'm showing. Okay? So that would be a consistent way to write it. And how would I basically find, let me call that VR actually, V sub R, to kind of be clear that I'm talking about the voltage across the resistor. Okay? How would I say what that value would be of V sub R relative to the other parameters that I have on that circuit? It should just be equal to I times R, right? That is a straight up application of Ohm's law, right? All it is just going to be I times R. Super. But what amount of power is going to be dissipated, assuming we don't have any of these relationships yet, and all we know is just our basic one that we looked at last time where it was voltage times current, right? How much power is going to be dissipated in this resistor if all you know is that it's going to be voltage times current? Okay, I'll call that power P sub R for the power dissipated in the resistor. It is just going to be equal to voltage, which we just identified was IR, right, times the current, which is going to be what? I. Okay, and that may not be the cleanest, most convenient way to write it, so I'm going to say that P sub R is going to be equal to I squared R. So if you know the current flowing through a given element, and you know the resistance value, I should say it's a resistor specifically, right? If you know the current flowing through a resistor, and you know the resistance value, that's all you need to know how much power is being dissipated in that element. Okay? Now, what about the case of a voltage being applied across a resistor? So this is a kind of a unique circuit in that you'll notice it really looks exactly the same except for what kind of source I put on there, right? It's unique in the fact that it is a single loop, yes, that's what we identified over here, but it's also another different category of circuit called a pair of nodes. A single node pair is sometimes what people call this, right? A single node pair. Where are the nodes? I've got one node up here, and I've got one node down here. Now, one of the things that we know about nodes is that anywhere you look in those nodes, you are going to have the same voltage. In other words, if I had a multimeter sitting here, and I could stick that multimeter at any point along either of the nodes, the multimeter, which is reading voltage, should read the same voltage regardless of where on each of those nodes I put my probe, right? So again, I should put this caveat in there. That assumes that you have zero resistance conductors, okay? But we are assuming that, so we can make that statement, okay? So that being the case, we know that the voltage immediately out of this voltage source is going to be V, but that also means that anywhere else we look on this pair of nodes, the voltage across those two pair of nodes is also going to be V. So that means I could go over here and say, I choose that position and that position right there and say that is still a voltage of V across those two spots, right? In the same polarity as I had for my source. Okay? Now, because I now know the voltage and the resistance, is it possible for me to figure out, just based on, again, Ohm's law, what the current should be that flows, I'll call that I sub R, the current that flows through that resistor? Okay? And how would you do that? Yeah, V over R. Simple, right? V equals IR, you rearrange that just a little bit, you got V over R. Okay? So that's all well and good. How do I know how much power is dissipated in that resistor? Our basic equation is always voltage times current, right? Okay, so we're still going to do that. So you say PR is going to be equal to voltage, which I know is V, multiplied by current, IR. But what is IR? Okay, I just said that was V over R, so V times V over R. And from that, I can simplify it a little bit and say this is just going to be equal to V squared over R. So what we're saying is, if you have a resistor and you know its resistance value, and you know the voltage put across that resistor, then you can tell me how much power that resistor is dissipating. Yes, sir? Okay. I think the point of confusion may be coming if you take your two probes of your multimeter in the case of looking at, maybe across two different nodes, right? And you're trying to kind of prove to yourself mentally that it really would be the same voltage regardless of anywhere we put it on that node or across those two nodes. It is a fundamentally different thing for you to pick up one of those probes and stick it on the same node as you just came from, right? In other words, they're now both on the yellow node or both on the blue node. Okay, so let me ask you, what would you expect the multimeter to read if you put both probes on the yellow or both probes on the blue? Either one of those cases. You'd expect it to read 0 volts. Why? Okay, there won't be any voltage drop. We can actually think to ourselves why that's the case in terms of Ohm's law. Okay, I said a second ago, we are going to assume all of these wires have 0 resistance, right? So that essentially, if the wire is 0 resistance, that means V over I equals 0. Okay? If V over I is equal to 0, what's the only way that can happen? For V to be 0. Right? I guess you could say I would be infinite. That doesn't happen, but V can be 0, right? So what we're saying there is that we should see 0 volts regardless of where we stick our probes on the same node. But if we go from node to another node, right, it doesn't matter where in either of those nodes we measure, we should see the same voltage. Yes, sir? Yes. So he's saying, won't there be a voltage drop across the resistor? I would say absolutely, but keep in mind the resistor bridges across two different nodes. So there can be a voltage difference from the yellow to the blue. That won't be 0. Right? So there will be a voltage drop there. There just won't be a voltage drop if I took my meter, right, and I took one probe and I put it there and another probe and I put it right there. I would see 0 volts, right? But if I took this probe and I stuck it down there, now I'm going to see a voltage of V. Okay, so voltage, let me make sure we clear this up. Voltage is a parameter that only has meaning for one place relative to another. You need two locations in order for voltage to have meaning, right? It has to be something relative to something else, right? And so my point I was trying to make is that it doesn't matter if I take this probe here and put it there and this one and put it there, or take this upper one and put it here, right? It doesn't matter where along that yellow node I put that probe, I'm always going to get the same voltage across there, and it's going to be the voltage that is across that resistor. The reason for that is that we're assuming 0 resistance in the wires themselves. So there will be 0 voltage drop as you traverse along the yellow node, 0 voltage drop as you traverse along the blue node. The only place where you're going to drop voltage is literally right across the resistor. We can talk about it more. I think Yes, got a couple more hands back here. If there was a voltage drop across the wires, would the multimeter read something was just the question. And the answer is yes, there would. Yes, it would. Right? As a matter of fact, that is a technique that is sometimes used in order to measure the amount of current flowing through a wire. Is you go ahead and you create a wire where it has a very low but known resistance, right? So it's not messing with the rest of the circuit too much because there's a very low resistance, but it's one that's very low and it's known, and then you measure the amount of voltage on that little segment of wire. You can, from that, back out how much current is flowing on that segment of wire, even though what you're measuring is a tiny little voltage drop across that little piece of wire. But I don't want that to confuse us in here, because in here, every time we draw a wire, we are going to assume that there is zero resistance in that wire. It makes our lives a lot easier in that way. Yes?
I know you said the circuit on the right says a single node circuit, so...
Single node pair. Yeah.
How is the one on the left?
It is not different. So this is a very unique circuit in that there's two elements. We can view it as being just a single loop. That's one perspective we can view it in, and we can see it as being a single node pair. It is both. Yeah, they are both, right? But, you know, I had to kind of think of it in one way to do one of the analyses and think of it in the other way to do the other analysis, right? You will see other examples of single node pairs, and you will see other examples of single loops also. They tend to be relatively simpler circuits to work on, either of those two options. So they're not uncommon to see them. This is I guess, the point of intersection between those two possibilities of types of circuits. Okay. Any other questions about this stuff before we move on? All right.